Have you ever thought that the ground beneath your feet could be a history book? Well, today we're going to play detective. We're uncovering a story of chemistry, climate, and time, told by the ground itself. So let's start digging for some clues.
So get this, in some forests, especially in the colder parts of the world, if you were to take a slice out of the ground, it would look just like this, these distinct, almost painted layers. You've got this pale, grayish slice on top of a rich, reddish-brown one. It's beautiful, right? But the mystery we're solving today is, what in the world is powerful enough to separate soil so perfectly?
Every good detective story starts by surveying the scene. So before we do anything else, we have to understand the very specific environment where this kind of soil is created.
Okay, so picture this. Our scene is a cold, damp place. Think northern forests. You've got a ton of rain or snowmelt, so it's always wet. And, crucially, the main players on the scene are pine trees. These three conditions, right here, are the essential ingredients for our soil story to even begin.
Now, the official scientific name for what's happening is podzolization. It's a mouthful, I know, but the basic idea is actually pretty simple. At its heart, it's just a washing process. Acidic water acts like a solvent, pulling minerals out of the topsoil and then dropping them off deeper down. This separation is what creates those really dramatic layers, or horizons as they're called.
So, we know we need acidic water for this to happen, but where does all that acid even come from? Well, the answer introduces our prime suspect, the real agent of change that kicks this whole reaction off.
That's right. This entire, massive, landscape-altering process begins with something as small and as simple as a pine needle. Kinda wild, huh?
And here's the connection. Pine needles, just by their very nature, are acidic. Now in that cold, damp climate we talked about, they decompose really, really slowly. So they just pile up, creating this thick, dark, spongy top layer called more humus, which is, you guessed it, intensely acidic. This becomes our chemical starting block for everything that follows.
With that acidic layer in place, it is time for the main event. This is where the chemistry really gets moving, and the soil starts its incredible transformation.
So here's how it works. When rain falls, it has to filter through that super acidic more humus. As it does, the water itself becomes a weak acid. And this acidic solution is surprisingly powerful. As it seeps down, it dissolves key minerals and, this is important, iron oxides. That's the stuff that gives soil its color. It also physically picks up and carries away the tiniest clay particles, leaving the bigger, sandier bits behind. After all of that washing and dissolving and carrying away, what are we left with? Well, let's look at the evidence. The soil profile this whole process leaves behind, one very distinctive layer at a time. First up is that top layer, what scientists call the A horizon. The best way to think of this is as the zone of loss. It's defined not by what it has, but by everything that's been stolen from it.
The evidence here is just crystal clear. Its color is this pale, almost ashy gray because all those iron oxides that would normally make it brown or red have been completely washed out. Its texture feels sandy because all the finer clay bits have been carried away. And really critically, it's nutrient poor. This is a huge deal because it creates a really tough environment for a lot of plants to grow in. Life has to adapt to a topsoil that's had its vitality completely stripped away.
So where do all those washed out materials actually go? They don't just sink forever. Often, they hit a stopping point where they build up and form this hard, dense layer called an iron pan. It acts like a collection tray for all those iron oxides and becomes a barrier, making it hard for water to drain. It really separates the world above from the world below.
And right below that iron pan is our next layer, the B horizon. And you know, if the A horizon was the zone of loss, this is definitely the zone of collection. Pretty much everything that was washed out from above ends up right here.
This layer is the complete opposite of the one above it. Its color is this rich reddish brown, and that's literally from all those iron oxides that have piled up and are now essentially rusting. It's dense, it's packed with clay, and it's full of all the nutrients that were stripped from the A horizon. When you see them side by side like this, the story is just perfect. The top A horizon is left gray, sandy, and poor. Meanwhile, the B horizon right below it becomes reddish-brown, dense, and rich. It's a perfect mirror image, a story of give and take, written right into the earth itself. But there's one final piece to our puzzle. Why do these layers stay so perfectly separate? I mean, you'd think over time they've just mixed back together, right? What's going on? Well, the secret actually lies in what isn't happening.
First, it's just too cold for critters like earthworms that would normally churn and mix the soil. Second, in this constantly damp climate, there's not much evaporation, so you don't have water being pulled upwards, which would bring minerals back to the top. And finally, pine trees themselves tend to have shallow roots that stay up in that poor A horizon. They aren't digging deep to pull nutrients back up, so that sharp separation gets locked in place.
So let's just put all the clues together one last time. Our detective story starts with the right setting, a cold pine forest. This creates that acidic top layer, which then fuels an intense washing process called leaching. This process separates the soil into a poor A horizon and a rich B horizon, and the lack of mixing keeps that profile locked firmly in place. Case closed.
At the end of the day, a podzol isn't just dirt. It's a physical record. It's a living history book. It tells you exactly what the climate was like, how much rain there was, and what kind of forest has dominated that landscape for centuries. It's a story written in layers of sand and clay.
Which really just leaves us with one final thought. We've decoded the story of this particular soil, but every soil everywhere tells a story. So the next time you're outside, what clues can you find? What story is the ground right under your own feet trying to tell you?